let's get started for today, and we're going to first finish talking about the beta distribution. If you remember why we came to this point is that when we were dealing with discrete prior distributions with a proportion, we realized that there are certain limitations, right? If you don't specify a particular value for the proportion P in the prior distribution, then by Bayes' rule, there will never, like that particular value will never show up in the posterior just because of how we're updating it. So that will be a limitation of thinking using the discrete prior distribution, even though overall it's pretty intuitive. So what we're going to do, like what we talked about last time, is we're going to introduce this new distribution here. We call it beta distribution. It's for a random variable falling between 0 and 1, so it's pretty ideal as a prior distribution for a proportion. And we use the notation A and B, both of them what we call shape parameters. And it's a continuous density, so you will see the PDF as what we show here in equation 12. And so for now, you know that, well, there's this constant 1 over beta AB or BAB here. Don't worry too much about it, like how to compute it for now, because later you will see that when we're trying to use Bayes' rule of the continuous version to produce the posterior distribution, you will see that it's a normalizing constant that we don't have to deal with much. Okay, so we can always just leave capital B, parenthesis A, comma B, closing parenthesis, as a normalizing constant in front of it. Okay? And just so you know, the constant is important. That we don't need to know how to like exactly compute it, but it's important here in the density because the whole F, I would say, integrating over P is going to be 1. So that's a proper density function. Okay, and that's what this 1 over B AB is used for there. Okay, so that's all we need to know now, and later you will see that we're always just going to write capital B AB there. And the key is the beta distribution is a proper distribution density that will be useful because it covers from 0 to 1 and it integrates to 1. Okay. And also last time we talked about that the uniform, the continuous uniform between 0 and 1 is a special case of beta. So you can always just write uniform 0, 1 is equivalent to beta 1, 1. And later you will see that, well, even though sometimes you might want to give a uniform prior for the P, we're still going to work with beta 1, 1 because everything later you will see is going to be more straightforward in terms of deriving the posterior. Okay. So we also, I guess, last time could show you all 9 different curves here. And you see that they all have different shape parameters. So 0.5, 0.5 for the first one. And this is the beta 1, 1, which is the uniform. And right, so between 0 and 1. So yes, all of this between 0 and 1. And then for this density is at 1 over here. Okay. And there are other ones here that I just want to give us a chance to talk to you later. Next to you, just to maybe select 1 or 2, just to describe, based on the shape of this particular beta prior, what do you think the particular prior belief is being conveyed? Okay? So uniform, we know that, which is in the middle, that is equally likely between 0 and 1, right? And you see some other shapes. So maybe you will not use them later, but still, I think it's a good chance now just to discuss and then think about how this shape is telling you. If you're going to use this prior for the P, what does it mean? Okay, what kind of prior opinion is trying to represent here? Okay, so let's take a break. I mean, you can one you picked, and then just maybe just talk about what you think. The beta prior that you pick is representing a particular type of prior belief. Yeah, anything is welcome, and we can discuss and develop. Yeah, no.
Yeah, we said for the beta with parameters 4 and 2.
4 and 2, so I guess this one?
Yeah, I mean, it's kind of, we've already kind of gone over it, but like, it's like if the values are like Monday, Tuesday, Wednesday, Thursday, and Friday, and then Sunday, you kind of see people would probably want to go out more towards the end of the weekend, and then all of a sudden, like the probability of then going out on Sunday drops way low, so.
Agree? Yeah,
I'm wondering what the x-axis is.
Yeah, good point. I was about to say, yeah. So, yes, okay. So I guess, so first of all, the x-axis should represent the proportion p, okay? And in fact, because of the setup that we did for this particular problem, it's going to be the proportion of, proportion of choosing Friday. Okay. So, but good point. I mean, because actually sometimes like a curve like this, you might think, okay, if it's going from left to Monday to the right to Sunday, then that's showing that kind of like choices over the 7 days. But because we're working with proportions, so we intentionally actually convert the problem into a proportion, right? Like say the survey was given out, I think, hypothetically at the beginning, we're saying that it's just going to choose your favorite day, but then we convert the problem into a proportion problem because we work on the proportion itself, and it's a proportion for Friday. So in this case, this will be from 0 to 1, and the x-axis is talking about the proportion that you think Friday will be chosen. Right? So if that is the case, what do you think beta 42 is representing? It's being picked around this number, right? So I'm guessing, okay, we probably can, oh yeah, 0.75, I think, because it's from 0 to 1. So beta 42 is saying that P, the proportion of choosing Friday, is going to be the highest around 75%, okay? But it's still covering the entire space from 0 to 1, right? And I guess it's a longer curve to the, longer tail, I would say, to the left, right? So you gradually, like your prior belief of this P is slowly going up. When you get to 0.75, that is the highest prior probability, and then it goes down to 0. Goes down to 0 for 1. Okay? So this is overall, I would say, thinking that, well, it's very unlikely. You don't think that the value is going to be too large or too small, okay? But you think it's going to be centered around 75%. And then gradually going down to both ends.
Mm-hmm. How do you know it's 0.75?
Yeah, well, I just realized because this was being cut off. And what I can see, I don't see numbers either, but I can see that the x-axis, you can see it from here as well. That is from 0, like this is from 0 to 1, and there are 3 points here. So I thought it's 75%. Yeah. So, well, you can say around 80%, it doesn't matter, but it's mostly like, it's more concentrated around closer to 1 value of the P, like the proportion, and going down to both ends. Okay. Any other choices that you want to talk about? Anything? If you were to choose a prior for this P, that is the proportion of choosing Friday, which one you think might match your belief most closely? Yeah, that will break for 1 minute. So yeah, so before we hear from some of you, I just want to mention again that all of this curve is talking about, so x-axis is the range of the random variables. Okay, so in this case it's P. So the x-axis goes from 0 to 1, and it's for the value of P. Okay. The y-axis is what we write FP, is what we wrote earlier before, is the density of P. Okay, so so we're still working on prior, nothing about the posterior of the data yet. We focus on thinking about different choices of priors at this moment. Okay. So anybody wants to offer what you think? Yeah, Josh?
I thought the first distribution kind of makes sense because people who usually eat out a lot. People who usually don't eat out at all. So they're kind of like concentrated on both extremes.
Mm-hmm. Yeah, so the first curve, beta 0.5, is definitely talking about is not likely at all to be somewhere like close to 0.5 or like anything in between, but it's likely to be very small or very large. So if I just to refine your statement a little bit more, I think because it's talking about the proportional Friday, so I think we probably just need to be careful, like, well, this is representing a belief that we think it's either very likely or very unlikely. any person gonna choose Friday. Okay, so it's not just eating out overall,
Right.
but it's choosing Friday. Okay, good. Anything else? Yes.
We set the one beta 4.2, so it's kind of similar to what we were saying in class, except we set that like the peak should probably be a little bit to the left. We thought it was like a little too high.
That is a little too high. Yeah,
but
so
yeah.
I guess like the peak going to the left a little bit more, maybe more symmetric. Okay. Carly?
We thought that maybe if beta 4.2 was flipped, like beta 2.4, so that it was very unlikely to be like less than 0.25, but most likely to be 0.25, and then somewhat likely to be bigger than 0.25 would be good.
Good point. So this is also touching upon, well, if we do beta 2.4, what we're gonna see, right? I don't know the answer to on the top of my head, but I'm guessing yes. So later in the course, like in this chapter, you will see that the A and B, the two shape parameters, we can also, so right now we're just like plotting random ones, and then we're gonna see how they look like. Later we're gonna see, I guess, interpretation of A and B in terms of your prior belief. And so just a little preview here that right now 4.2, like 4, the first shape parameter A, is representing what we call the prior success sample size. Like in your prior, how many success you think there should be, okay? And then the second parameter B, in this case the 4.2, is 2, and then that's representing your prior belief of how many failures there should be, okay? So I think using that, so we will see why in a minute. But in here right now, especially being mentioned about, well, what if beta 2.4? So I think, I agree, I think it will be very likely just gonna flip the shape, because now you're moving from, so it's 4.2 to 2.4. So earlier you're thinking that, well, twice as likely you're gonna get a success, right? But now if you go to beta 2.4, it's twice as likely you're gonna get a failure. Okay? So it's the concentration will be moving to the left, and I think right about 25%, and then the shape will just move accordingly. So it's going to be a little bit symmetric, as you will see. And so for now, just because this is being mentioned from 4.2 to 2.4, so I mentioned the A and B, the shape parameters representing prior belief and then sample sizes. Later, once we cover all of the detail, we're going to see why that is the case. Okay? But for now, you can think in that way that, well, 4 is representing how many successes that I think in the prior, and then 2 is representing how many failures I think in the prior. Okay, good. All right. I left a homework. I mean, for the second homework, I left a couple of exercises for you to just discuss a little bit more about, well, how different prior choices here is representing your belief. All right. So again, we know that for the prior opinion, we need to come up with the values of P and also associated probabilities. As you can see that if we're just going to try to choose random choices of A and B and then plot them, it will be a little bit hard to find the correct one that you really like. So the solution that we're going to provide for this class is, well, instead of thinking about A and B, the values of them directly, we can think about specifying a prior by specifying the quantiles of the distribution. Okay, so first of all, quantiles about rank order of values. So the famous, or the one that people know mostly, I guess, is the middle quantile, the middle 50th quantile, which is the median. Okay? So this is saying that you are sorting the value. You have a sequence of values, you're sorting, and then you're choosing the middle value, and that's the median. So for here, what we're going to cover is this beta quantile function. Again, this is also coming from the prop-based package that is written for this material. And it's going to input a probability measure P and output the value of X such that you're able to get the quantile of that value. So this is, some of you probably have experience dealing with quantile in the past. So for example, if we're working with beta 710, this is just an example here, that if we choose the quantile to be 50%, which is trying to find the median, then the median for this particular beta 710 will be the output from this function, which is 0.408. Okay, So this is a way that, well, even though I don't know exactly how to choose A and B per se, but I can actually think about the quantiles of the distribution that I want my beta prior to have. So let's just practice here. So in this case, you will see that the, sorry about the size, it's a little bit hard to put everything on the screen. But overall, if you run this beta quantile function, so in here you will see that you fit in your shape parameters. In this case, we'll just do 7 and 10 as a demonstration. And then we're trying to get the middle 50, which is the 50th percentile, which is the median. Then it will give us the particular number that will reach that median value. Okay. So beta quantile can get you 1, and you can actually specify beta distribution or beta prior distribution through a different, like a sequence of numbers or quantile that can help you define clearly which beta prior that you want to use. So for us, let's think about specifying 2 quantiles, and then the function will help you to do the beta curve that matches with this quantile. That's the beta.select function. So as a demonstration here, suppose we think that the median, which is the 50th quantile, the value for B, which is the proportion, we think is about 55%. Okay? And let's say also we think the 90th quantile is about 0.8. Okay, so this is, I guess, less extreme than what we saw earlier with beta 4.2, right? Beta 4.2 is even closer, I think, to 1. So if we make this decision, you can come up with other ones, which we will do as a small exercise in a minute. But for now, we do 50% with 0.55, and then 90% with 0.8. Then if you use the beta.select function in this way, it's going to give you the value of the 2 shape parameters. Okay? So this is giving you the best matching beta prior for if you're going to specify 2 quantiles and then let the function decide it for you. All right, so I guess not everybody brought a computer, which is fine. And this are 2 exercises here that later you can take time to do it if you want. One thing is verify that this beta distribution that we came up with, 3.06 and 2.56, they are indeed having the 50th quantile to be 0.55 and then the 90th quantile to be 0.8. The hint for you is use the beta quantile function to make sure that it is matching. Okay. The second one is come up with your own beta prior distribution and share with your neighbors. So it's okay. I don't think we're going to do it in class today. I should mention earlier that people can bring a laptop, but next time I'll make sure that you announce it early so we can actually do something class. Okay. But overall, take the time later after class just to verify this and also just get sorted out the ideas about quantile. Because later on, especially when we go to other functions of beta, well, quantile and then percentile and then doing all that, like what is the input, what is the output, I think at the beginning can be a little bit confusing. So I think it's a good practice regardless. All right, so that's all for the beta distribution itself. And soon we're going to just, after this, we're going to move to how to update the beta prior to a posterior distribution. So just to recap here, we covered a particular continuous distribution that is suitable for a quantity between 0 and 1. Okay? It's continuous, so it covers the entire space. And now we learned about the PDF and then how to choose the beta prior. So the problem for us is the likelihood or the data will still be binomial, right? Just like in the discrete case, because that doesn't depend on what kind of prior choice you're doing. We think that as a binomial experiment, so that doesn't change. And now we have a different prior distribution here with a particular continuous PDF. The question now becomes, okay, how can we use Bayes' rule to derive the posterior that we want? Okay, so this is what we're going to do next.